All right, welcome. This is going to be talking about the graphical displays of categorical data. So in other words, what's the best way to represent categorical data? The three rules of data analysis you do need to know is make a picture, make a picture, make a picture, and make a correct picture. Don't screw around and make these things horrible. One of the most simplest one is to make a frequency table. Is just basically just piling all the information out there. And in the book they talk about the Titanic and they use the information from there. So in the frequency table they list the first class passengers, the second class passengers, third class, and the crew, and it's just basically all set up pretty easily. Okay. So basically it looks like this. Alright, let's try it. Nope. Basically just represented as this. So there's our frequency table. It just lists everything we need, and we just have everything all set up, and it's just simple stuff. So just by taking a look at this, you're going to notice crew's the largest number, but if you add up these three together, the amount of passengers outweighed the crew by 2 to 1. So that's something important. Okay, now that doesn't give us a whole bunch of stuff. We could make bar graphs out of it. We can make pie charts just to show all this stuff. I mean, it's all kinds of interesting stuff that we can actually do. Okay, so if we wanted to do a bar chart. Now, if you do a bar chart, you do need to pay attention to the fact that you need to label the axes and everything. So as you can see, the majority of the people on the board the Titanic were poor. Okay, so that's interesting. You can see a visual of that. Okay, or you could do a pie chart, and you could do, now pie charts are unique in that they give you relation and proportion. Okay, so it's something very important by that. Okay, if you want to give the relationship in terms of percentage of the people, you can see crew and third class were pretty close. If you really want to draw people's attention to that proportion, use a pie chart. If you wanted to draw people's attention to the relative proportion of people, you would probably use a bar chart. Okay, so it's up to you. You do have to pay attention to how your graph works. So for example, if you're showing a graph that looks like this in your book, okay, and it looks like something like this, as you can see, people are going to think, oh, there's so many crew people on there. Well, you have to pay attention to the relative size, and these graphs are infamous for appearing in USA Today. They'll like, oh, it's really big and it's like really small and blah blah blah. And oh man, I think there's a website, History of Bad Data, so you can go on there and you can look and just see some horrible data examples that just work awful. I mean, it's just like you're just shaking your head. You're like, oh my gosh, this is the worst. Okay, another one that shows up is a contingency table, and it could also be used as a distribution table. Okay, so a contingency table would just have this information in there, the alive and dead people, and list them by first, second, third, and crew. And then a distribution table would also have the totals, so the total amount of crew or alive and dead, and the total amount of each passengers and the total amount of people. So that's very helpful to work with, right there. All right, another one we could do. You could also represent percentages and everything, so you could also see that in a contingency slash distribution table, so you can look at that stuff. So I mean, here's what it looks like. It's just pretty simple. Just set up the spread so you can see the percentages. Just very interesting to see. I do know, and this was interesting. When we were doing getting ready for the year, one of the stats teachers brought up like conditional probability and stuff, especially using contingency tables. And she found out that if you were more likely to be male, you were more likely to die if you were on the Titanic than if you were a female. So there's a reason why Jack died at the end of Titanic, because he was trying to save the ladies. And who said chivalry isn't dead? So that's that. All right, there's also things called conditional distributions. Okay. All right, and that just kind of it kind of mashes the two together. It's a really interesting question to ask, whether the chance of surviving the Titanic sinking depended on ticket class. And as you can see, your chances of being alive were greatest if you were crew or first class, not as great as if you were second class. That brings up some questions like what happened. But then if we look at second class, dead, 11% chance of dying, whereas 35% chance of surviving. You sit there and ask yourself some questions, All right, so that's the big thing. Real fast, segmented bar charts. You could display the Titanic information by dividing up the bars rather than in circles. The resulting thing is called a segmented bar chart. Okay. Here's what it looks like. Okay, and it just gives you it gives you striation. You can clearly see the distributions of ticket classes are different, indicating again that the survival was not independent of class. So in other words, it was dependent. If you survived, you were probably in first class. If you didn't survive, you were probably in third or a crew. So this one's a little bit better picture to see than the conditional one. So it depends on what you want to display the data as, and just to go with that. Okay, things that can go wrong. Do not violate the area principle. Okay, that's huge, huge, you guys. Okay. This is probably the most common mistake in graphical data. It often misrepresents the cause of artistic presentation. Here, for example, are two displays of the data. Okay, the one on the left looks pretty, doesn't it? But it shows a pie chart on a slanted. It violates the area principle and makes much more difficult to compare the fractions. Okay, so that's why you always want to have an overhead view when looking at it. Keep it honest. Here's a pie chart that displays the data of the percentages of high school students who engage in specific dangerous behavior. Okay, what's wrong with this? Okay, well, take a look at the percentages. I'll give you a hint. They don't add up to 100%. So someone really screwed up on this one. So you have to just keep your information honest. You just have to sit there and just work with it and just go through it, okay? All right, don't confuse similar sounding percentages. For example, these percentages sound similar but are different. The percentages of passengers who were both on first class and survived, that'd be 203 out of 2,201, or 9.4%. The percentage of first class passengers who survived is 203 out of 325, or 62.5%. And the percentage of survivors who were in first class, that is 203 out of 711, or 28.6%. In each instance, pay attention to the who implicitly defined by the phrase. Often there is a restriction to a smaller group, all aboard the Titanic, those in first class and those who survived respectively, before a percentage is found. Your discussion of the results must make these differences clear. Okay, so you have to be very clear on what you're saying. Don't forget to look at the variables separately too. There's this thing you're going to learn at the end of the semester called Simpson's paradox, and it's huge that you look at the variables to see if there's something that's going on behind the story. Be sure to use enough individuals. If you use a small percentage, it's going to be a really huge problem. Okay, so please, 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 please take your time, look at this information, and just don't go nuts. Don't go, oh, I know everything, and just work on it from there. Okay? And don't overstate your case. Independence is an important concept, but it's rarely for two variables to be entirely independent. We can't conclude that one variable has no effect whatsoever or another. Usually all we know is that little effect was observed in our study. Other studies and groups under those other circumstances could find different results. Okay? And Simpson's paradox, do not use unfair or silly averages. Sometimes averages can be misleading, sometimes they just don't make sense at all. Be careful when averaging different variables that quantities you're averaging are comparable. The Centerville sign says it all. And the sign's over here to the left. Okay, but it says entering Centerville, established 1793, populations 7,943, elevation 710, average 3,482. Okay, well, you don't want to add those three numbers together and then find the average, because it doesn't make any sense. You don't want to average the year established, the population, and the elevation, because that just doesn't help at all. Okay. All right, you guys. That's it for the first three, or the graphical displays of categorical data. We'll talk more about quantitative data next time. Okay, thank you very much and have a great day.